Welcome to this explainer. We're diving straight into a microscopic battlefield today to uncover how our so-called miracle drugs are, well, literally losing the war. For decades, antibiotics have been our ultimate weapon, curing things that used to be fatal, making modern surgery even possible. But here's the thing. The enemy has been evolving. We are locked in this intense evolutionary arms race with bacteria, and right now, they're gaining ground. Just look at these stakes. Right now, more than 70% of bacteria causing hospital-acquired infections in the US are resistant to at least one drug we previously used to treat them. 70%. This isn't just some theoretical sci-fi future problem, it's happening in our hospitals right this second. We're actually seeing strains of Enterococci, Pseudomonas, and Enterobacter that are resistant to absolutely all available antibiotics. No way around it, that is terrifying.
Section 1. The end of antibiotics. The stakes of microbial warfare.
Section 2. How bacteria fight back. Inside the enemy's defense systems.
Okay, let's get into the mechanics of this. For an antibiotic to actually work, it has to do three things flawlessly. First, it has to reach its target within the bacteria. Second, it has to remain active. And third, it has to bind properly to interfere with the cell's function. But bacteria have evolved three distinct military-style defense tactics to disrupt this exact process. They either stop the drug from reaching the target, inactivate it entirely, or fundamentally alter the target itself.
Let's look at the very first tactic, blocking entry. So gram-negative bacteria have this outer membrane that acts like a massive fortress wall. Small molecules, like our antibiotic drugs, have to enter through these specific little protein channels called porins. But bacteria are smart. By mutating, removing, or changing these favored porin channels, they essentially shut the gates. They prevent the drug from ever getting inside, meaning the antibiotic concentration literally never reaches a lethal level.
But what if the drug does manage to sneak inside? Well, bacteria have a backup plan, and it's called efflux pumps. Imagine these acting just like bouncers at an exclusive nightclub. They physically grab the antibiotic and throw it right back out of the cell. These specialized transport systems are unbelievably effective and are responsible for resisting a huge variety of drugs, things like tetracyclines, macrolides, and fluoroquinolones. They literally pump the drug out faster than it can diffuse in.
Now this brilliantly illustrates the second major defensive tactic, drug inactivation. Bacteria can actually produce special enzymes like beta-lactamase. You can think of these enzymes as a highly trained bomb squad. When a beta-lactam antibiotic, like, say, penicillin, enters the periplasmic space of the bacteria, this enzyme swoops in and literally dismantles it. It hydrolyzes the antibiotic, completely neutralizing the threat before it can cause any harm whatsoever to the bacterial cell.
The third defense is target alteration. And this is exactly like changing the locks on a door, so the antibiotic's key just doesn't fit anymore. Even if the drug gets inside and even if it avoids the bomb squad, it's totally useless if the target has shapeshifted. A really famous example of this tactic is used by methicillin-resistant Staphylococcus, or MRSA. They produce a modified, low-affinity penicillin-binding protein, so the antibiotic arrives, ready to work, but it just can't bind to its target to stop the bacteria from replicating.
Section 3. Passing on the resistance. The genetic intel exchange.
So, how does this spread? There are two main ways bacteria pass on this genetic intelligence. The first is vertical transfer. This is when random mutations give a single cell a survival advantage, and it just passes that winning trait down to its daughter cells when it divides. Simple enough, right? But the far more dangerous and rapid method is horizontal gene transfer. This is where bacteria literally share their resistance blueprints with completely unrelated neighbors in their environment. It's like an open-source network for survival.
And horizontal transfer happens in three pretty incredible ways. First up, there's transduction, which uses viruses called phages as accidental couriers to carry resistance genes from one bacteria to another. Second is transformation. This is wild. A bacteria simply absorbs free-floating DNA left behind by dead cells in the environment. And third is conjugation, which is direct peer-to-peer sharing.
Let's zoom in on conjugation because it is absolutely fascinating. It functions exactly like a microscopic file-sharing network. Two bacteria physically connect via a bridge, and through this bridge they transfer plasmids, these mobile little circles of DNA that often encode multiple resistance genes at once. So, in a single, highly efficient event, a completely vulnerable, harmless bacteria can suddenly acquire the blueprints to fight off multiple classes of antibiotics just by touching a resistant neighbor. It's a real game changer.
Section 4. Counter tactics and solutions. How humans can fight back.
One incredibly powerful clinical strategy we have is combination therapy. Instead of using just one drug, we hit the bacteria with multiple different weapons simultaneously. Weapons with entirely different mechanisms of action. Why do we do this? Well, because the probability of a bacteria spontaneously mutating to resist two completely different drugs at the exact same time is astronomically low. This synergistic approach is absolutely critical for effectively treating stubborn infections like tuberculosis and for stopping resistant mutants from taking over.
But listen, the most important tactic in this war isn't just better chemistry, it's human behavior. Misuse of antibiotics applies massive selective pressure that basically turns our bodies into a training ground for these superbugs. Prescribing antibiotics for viral infections, like the common cold or the flu, where they literally do zero good, is a huge problem. So is improper dosing, where a subtherapeutic level fails to kill the bacteria but gives them just enough exposure to learn and adapt. Furthermore, relying on drugs alone while ignoring physical solutions, like the surgical drainage of an abscess, creates the perfect safe haven for bacteria to multiply and mutate.
The message here is crystal clear, perfectly summarized by this quote: "The rampant spread of antibiotic resistance mandates a more responsible approach to antibiotic use." If we want to preserve the incredible, life-saving gains of modern infectious disease treatment, clinicians and patients must be far wiser and far more selective with how we deploy these drugs. We have to identify the specific bacteria quickly and use the narrowest spectrum antibiotic possible, rather than just carpet bombing the entire microbiome. So I want to leave you with this to think about as we wrap up this explainer. Are we truly prepared for a post-antibiotic world? A world where a simple scratch or a routine surgery could once again become a death sentence? And maybe more importantly, what can you do, starting today, to stop feeding the enemy's intel network? This arms race is happening inside us right now. It is high time we start fighting smarter.